Student, I, Soumen sir, lecturer in mechanical engineering. Today we know what is bending equation. It is also known as Flexural Formula. Chapter name Bending Stress in Beams. This equation based on the theory of pure bending. Pure bending or simple bending means shear stress are not to be considered. No shearing action takes only bending action. This is initial position of beam. Beam is supported at end A and end B. NL is the neutral layer. This is the final position of beam. Length of beam under action of bending moment. When load W act at center, bending of beam, it is bent like curve. R is the radius of curve NL. Here, this is the cross section of beam. NA is the neutral axis. Y, distance of topmost layer from neutral axis NA. Bending of a simply supported beam. Maximum compression developed at topmost layer of the beam and maximum tension developed at bottommost layer of the beam. The layer NL, neutral layer, is neither compression nor in tension. Magnitude of bending stress is proportional to its distance from neutral layer or neutral axis. Upper portion increases compression stress gradually. At NA there is no stress up to topmost layer. Distance increases and chest compression chest also increases, and also at lower portion of NA distance increases and tensile stress increases. At bottommost layer there is maximum tension. This is the equation of pure bending. Here F equal to stress due to bending at a distance y from neutral axis NA. Any layer at a distance from NA. Unit is Newton per millimeter square. Y is the distance of layer subjected to bending from neutral axis NA. Here Y, distance of layer where bending stress are calculated. It is maybe upper portion of neutral layer or lower portion of the neutral layer. Distance is y. Now I equal to moment of inertia of the beam section about the neutral axis NA. This is the cross section of the beam. The unit of I, moment of inertia, is millimeter to the power 4. R, this is the R, radius of curvature of neutral layer of the deformed beam. Unit is millimeter. M is the bending moment or moment of resistance due to bending of this portion of the beam due to the action of load W at center. Bending moment or moment of resistance are created. Its unit is Newton millimeter. E equal to Young modulus or modulus of elasticity for beam material. For different material, E is different. Its unit is Newton per millimeter square. Okay. Now we learn bending stress distribution diagram for symmetric section. This is the rectangular section. This is hollow rectangular section. This is the circular section. This is the hollow circular section. This is I section, maybe T section. This is the NA neutral axis. All sections symmetrical about both x and y axis. NA is the neutral axis. This is the stress distribution diagram for simply supported beam. Above NA compressive stress, below NA tensile stress. At topmost layer maximum compression and bottommost layer maximum tension. From neutral axis, distance increases and compressive stress also increases. At topmost layer is maximum. Below NA, distance increases gradually and also tensile stress increases gradually. At bottommost layer, tensile stress is maximum. Okay. It is clear, my student. Thank you.